distribution function, and it actually wasn't in Cook and Torrance's paper either, and I figured it out by getting a copy of Cook's thesis when that paper was published, and then I wrote an introduction to that paper in a compilation of important papers, and here it is. So you can see here, maybe I give one more for this row. You can see written out basically the content of my last lecture, or at least the part of that that wasn't in the book. Okay, so are we ready here? So I just handed out some pages in Davis, and I'll give them to the people who are doing the TV, and they'll get them to you in Livermore. And I made an announcement on this board. You're going to mail me your homework, and the homework has to have at least an image, and I suggest it should have also the source files you've changed. I probably won't look at them if the image looks fine. And so this message says, put 275 in the subject line of your email. That way, when I get ready to grade them, they've come at disparate times. I can get them all together, not miss any, and do that in the future, too. So today I'm going to go back to some ideas we were talking about 2 classes before with the rendering equation. So let's see. I'll put it on this board. Basically, we're going to think of the light that's leaving a surface in a given direction as the sum of 2 components. The light that's emitted, if it's a light source, like a bulb or the sun or a hot stove or something, leaving the surface, plus the light that's reflected. I should start using the eraser instead of my back of my hand for correcting things, x in direction theta. And what we know is, let me copy the light emitted again. And now let me put in that integral over all the light that's coming in from all directions and reflect it. Right? That's how we included the bidirectional reflection function. So that is the integral over the hemisphere above point x. So here is point x. Here's a piece of a surface with a point x, and this light is reflecting in some direction theta, but it's scattering all light that comes in all other directions from direction capital psi, and we integrate it over the unit hemisphere above the point x on this surface, all possible directions that are coming, light hitting the front third of the surface. And that integral we had was the bidirectional reflection function at x for light coming to direction theta from direction psi. And it didn't matter what order we put them in because of frequency. Okay, times that light coming in, which means hitting x from direction psi. And then we had a cosine of an angle between that direction psi and the normal. Let me make where am I going to make the normal? Maybe here. To the surface. So it's this angle which the book writes as cosine of n at x and the direction psi. And then d solid angle for the incoming direction. Right? So we'll integrate because radiance is light per solid angle per unit surface area normal to the beam. So this cosine theta factor converts it into an irradiance on the surface. which may be slanted with respect to the incoming beam. There's some angle between them. And then this is an integral over all this hemisphere. So this is what we had, I guess it was last Friday. Okay, so if you look at this equation, this says, maybe I'll write it here, light, again, x, going out in direction theta, depends on light at a bunch of other surfaces, really, right? Because this is light coming from other surfaces at other points. Right? This is outgoing light, this is incoming light, but we can actually get it in terms of outgoing light by finding out where the ray from x in direction psi intersects another surface. If it doesn't, it goes out into outer space, there's no incoming light. But usually, if we have an enclosed model, every direction will intersect something, like the wall of this room. And so here's the point y, and here is the light leaving y in direction minus psi, right? It's the opposite direction. So this integral here, we can write also as the integral over omega x with this fr. But we have to find the point y, and we can say y, we can take this ray with origin x, so r x psi is the ray that starts out at x as its ray origin, and with this as its unit vector. And we can say, actually, this notation means more than that. This notation actually means the point y, the first point, if any, that ray intersects another surface. And so for this L going to x from direction psi, we can say L at the point R x psi. It's hard for me to draw capital psi. Right, this is the point y here, and leaving in direction minus psi, cosine d omega psi. Now we have leaving light. So this is using the principle that was proved in the book that I didn't have time to talk about in class of the equivalence of radiance, no matter where along a straight line ray you measure it, as long as there's no absorption or objects blocking. And they calculate it out in terms of the flux starting from one surface element and hitting another surface element. And that flux is constant if there's nothing in between. And then by the definition of radiance and a little bit of algebra, if you follow the derivation in the book, it says that the radiance is the same, whether it's measured at this point or that point. And that's what I've used when I've done this substitution. Okay, so now we have an equation where if you say, suppose you know the radiance leaving all the surfaces, then this is a consistency equation that says something about the radiance leaving every point in your environment and going in every direction. So that's going to be your unknown that you want to solve for if you're trying to do global illumination. And this left-hand side has that unknown at a specific point and a specific direction, but it's expressed in this known quantity plus an integral over radiance at other points in other directions. So this is called a Fredholm integral equation of the second kind. And our goal in doing a global illumination is to try to find approximations to the solution of it. We could never find the exact solution because we could never even represent it on a computer, because a computer can store only a finite number of numbers, and this is a function of two continuous variables positioned all over the surfaces of the scene and directions, every direction over a hemisphere from each of these points. So at most you could sample it at a bunch of points or approximate it as, you know, a piecewise linear or a piecewise polynomial or a piecewise constant function. Okay, so what I'm going to do is I'm going to rewrite this light reflected integral that I had on that board. Maybe I should copy it now. Basically, this light reflected is the thing we're talking about now, because we know the light emitted. X goes to theta. And that's what I expressed as this integral from the other board. I want to get it on this board. The light at X, theta coming from psi and reflecting into theta. And now the light at the position where this ray from X in direction psi intersects another surface times cosine of normal at X and this ray direction psi. I missed a minus psi here, didn't I? So what I want to do is rewrite this as an integral over surfaces. In other words, instead of saying what is starting from direction psi, figure out what surface is intersected, I want to start with some dA y around y and do integrals over the surfaces in the scene. Well, if I'm going to do that, I have to know whether this point y is visible to X. In some cases, it may not be. There may be something in between. So the visibility between X and Y is 1 if Y is visible to X. That means if a ray between X and Y doesn't intersect any other intervening object along the way, and 0 otherwise. If that ray that's like a shadow ray, sort of it's a test ray, if it does intersect something before it gets to Y in the direction from Y to X, I mean from X to Y, then it's 0. So what I want to do is rewrite this integral as an integral over all the area of all the surfaces in the scene. So this capital A stands for all the surfaces in the scene. So it's really going to be a bunch of separate integrals, say an integral over that wall and an integral over that wall and an integral over my face, or however you can parameterize the integral. But you think of it as an integral over dA here, dAy. And that means we have to turn this dAy into one of these solid angles at X. Right? Because this current integral is d omega. In order to convert this integral, we have to see how we express d omega in terms of dA. And so we had that formula, d omega for psi is this dAy we want the area on a unit sphere, so we have to divide it by the square of the distance between X and Y, which I'm denoting by Rxy, because it's supposed to be area on a unit sphere, which is solid angle. And this area, if you think about this distance here, from here to here is Rxy. If this were actually, if the normal of this dAy pointed along the direction psi, that would be the right answer. But if it doesn't, right, and there's some angle between them, then we have a foreshortening. So times the cosine of the angle between the normal at y and the direction minus, let's see, why don't we think of it, let's take the direction from y to x. So the notation in the book, I guess, for that angle minus psi in question is the vector from y to x. Think of it as a unit vector in that direction. Right? That's the angle we're concerned with. And so that's the omega. And so now we can have this same fr at x going out in theta and coming in from the direction from x to y. Right? That's the direction of that psi. And now, instead of saying this is the y that ray first hits, we're going to say we're going to integrate over all y's on all surfaces, but we'll set to 0 the ones that don't get to x by multiplying by the visibility between x and y. Okay, and then we have a factor that depends on these cosines. This is cosine nx, and this is the vector xy. And then if I copy this terms here, cosine ny, and the direction y x, and then dA at y divided by rxy squared. Right? This much of it corresponds to d omega, and I put this one on there too. And so this quantity, this much of it, is called the geometry factor, gxy. If you read research papers, some other authors put the vxy in there too as part of the geometry factor, but our book doesn't. So basically, this integral then, if I grouped all that as a geometry factor, I would just get for my LR, I'd get the integral over all surfaces of this bidirectional affection function times Ly Vxy G, capital Gxy, dAy. So what we've done is we've changed an integral over solid angles at the point x to an integral over all surfaces in the scene of radiance leaving the surface. So that's another formulation of this reflected light. And if you rotate, this is, yeah, it's really, I said Ly, but it's really L, let me squeeze it in properly. It's L at the point y, leaving in the direction from y to x. Right? That's what I really meant here. I think did I have it? Yeah, this is the direction from y to x, and this is the point y. So now, the light at this point y might be, if this light was a light source, that would be emitted light. So what I'm going to do is I'm going to break up the light at y also in these two terms. That's just because I want to have a separate expression for the direct illumination. In other words, what is the contribution to light emitted from this surface if it were a light source? And that is what's going to give you the direct illumination, and it's going to include the shadow penumbra effects, but not the global bounces, which is the bounce light that actually got to y from yet another surface. And so for the direct illumination, from x reflected in direction theta, that's sort of what you'd be rendering if you were rendering like shadow effects from light sources. we could do that integral over the light sources. So we're going to integrate only over L of lights. And what we're going to integrate is this FR. I won't put all the angles in, but it's only going to be the emitted light at Y in the direction from Y to X. G of XY, V of XY. I got them in the wrong order. dA at Y, where now we're integrating only over the light sources, and we're integrating over the emitted light. So what we're going to be doing for the next few weeks is figuring out how to estimate that kind of integral. So if you were getting it at a very specific point, you might be able to do it geometrically. And in fact, historically, that was one of the first ways it was done in computer graphics. At every point you were shading by direct illumination, you would actually make polygons of all the light sources and then clip the light source polygon by the projection of every other polygon in the scene onto that light source plane. So you remove the parts that were hidden, and you would get another polygon that was left. And then if the BRDF was like a Lambert law or something simple, you could actually get this integral analytically. But the philosophy now is to get it by sampling. You represent a bunch of points on the light source. And one method is just saying, okay, let's just make, this ceiling lamp be like 20 points in a row, and this area diffuser, which I can see that looks more like a polygon instead of a single tube, be, maybe 10 by 10, 100 points. And you just illuminate it by all those point light sources. But that's not actually going to give you the correct shadow penumbra, especially if your points are like in rows across the light, right? Because if I think about the shadow, we've got so much light in this room, I can't see the shadow from a single light source. But if I have a bunch of rows of lights here, and I have points on the ground, and I have my piece of paper in between, there's some points on the ground which will see this many lights. These points, these points, these points will see that many. And then once I cross the threshold so that this point is visible, it's going to suddenly get brighter. And I'm going to get stripes of light. In fact, if you use too few light sources, you can really perceive it as just an image with a bunch of point light sources. And one solution to that is for every pixel, take a different collection of dots on the light source. So you could imagine sampling the light source in some sort of random way with different samples for every pixel. And then it still wouldn't be exactly accurate because you're still estimating this analytic integral by sampling. But what you would do is you turn this banding error into what would look like noise. Right? There's still, say if you only have 20 spots on the light source, there are only 20 different levels. But instead of being in a bunch of bands, the bands sort of get broken up by the noise, by the random placement of those dots. So that's going to be the philosophy of our Monte Carlo sampling that we're going to start. I'll have some time today to even start on it. And then you could do L indirect X coming out in direction theta. You might want to do that over the hemisphere of this FR L. And now this is the reflected light instead of the emitted light. And I guess, what was it? It was at the point R, X, psi, minus psi, cosine, nx, psi, d omega psi. So to sample that, if here is your point X you're shading on this surface, we take a hemisphere and shoot rays out in that hemisphere. They're like shadow rays. Just like to estimate this thing, we see if the point on the light is visible. Now we just shoot a ray out here and see it's not a shadow ray, it's just a ray, see where it hits. And that's that point Y, which I have here as where that ray hits. And, one way of, this, you have to do this, it's still an integral equation. You still have to figure out this recursively, which is sort of, one way to do that is to keep bouncing more and more until you eventually hit a light source. And then do the shading. Or you could say, okay, let's use Lambert law or some diffuse shading on the second bounces. So we'll assume the surfaces have diffuse shading, but they can sort of, so at this point you might just do the kind of illumination you do with the sum of the light sources. But if I had a red wall on this side wall, and it was illuminating by the light sources, and I was generating this wall, and I was tracing rays from here, and a bunch of them hit this wall, they would pick up some red color. And I would, even though this one I just shaded directly from the light source, I would get the rays that bounce here would pick up some red here from indirect illumination as well as the direct. And that's sort of a color bleeding effect that you get by global illumination. And we could do that by sampling this integral by the directions and then using some other way to get these. Or we could bounce, once we hit that wall, we could bounce again. And that's the path tracing that I also want you to do for the assignment after next. Not the next assignment, but the one after. You'll be sampling lights and you'll be sampling the global illumination environment. But what I want to start talking about today and next time is the mathematics between, the mathematics about how to compute an integral by sampling. And it's based on probability theory. So I'm going to start just with an introduction to probability theory. So an event. So first off, we're going to talk about discrete probabilities. When we only have a finite number of events, like a coin, you toss it, it could either come out heads or tails. Or if you roll a die, a single die, it has 6 faces to the cube. There are only 6 possibilities. So an event is one of those possibilities. So an event is the outcome of an experiment like flipping the coin or rolling the die, and a random variable assigns a number to each event. So if you put numbers on the faces of the die and say, if that face comes up, I'm going to say my random variable takes that number. Then instead of just events, I've actually got numbers out, and those are called random variables. So now the probability, if it's a random event, then every event has a probability. So every event, say I, has a probability P of I. And the random variable, say X, and the random, what I want to say, and X gets the value X of I corresponding to event I. Right now we have only a finite number of different events. Okay, so the properties of the probability is that the probability is some non-negative number between 0 and 1. Right? So the probability that the coin will be, an event is a way to describe the outcome. So we could say the probability of the event the die coming up with number 2 is a 6th if it's a fair die. But we could also make the event, in terms of looking at the outcome, say whether it's odd or even. Right? And so that would include 2, 4, and 6, and the probability would be a half. So events don't have to be, just, how can I say it? You can think of it depends on how you look at the experiment, basically. But, the event could also be that it's either 1, 2, 3, 4, 5, or 6. Then the probability would be 1 that one of them would happen. Or the event would be the probability that the die ends on its point, which is never going to happen. So that probability is 0. So the other thing is if you sum over all the events, pi, that has to add up to 1. Right? Because if you add them all together, it includes all the things that could happen, and one of them has to happen. So their probabilities have to add up to 1. Because probability really means the chances, the fraction of the events that you'd expect that one to be. So these are two properties of probability. For anybody who came late, on this board I had the notice, please put 275 in the subject line of the email with your homework, so I can find them all when it's time to grade them. Okay, so now the expected value of a random variable x is written as E of x, and that's the average that you'd expect that random variable to have if you rolled the die a lot of times. We could ask, what is the average of the score we're going to get? And so what that is the sum over I of the score on the ith event times the probability of that event happening. So for a die, pi equals 1/6 for I equals 1, 2, 3, 4, 5, or 6. Those are my 6 possible values of the random variable, 6 possible outcomes if I look at just what number comes up. And so it's going to be 1/6 times each of them of 1 plus 2 plus 3 plus 4 plus 5 plus 6. There's a formula for adding the first 6 consecutive numbers. For this many, it's just easier to add them. 1 and 2 is 3, and 3 is 6, and 4 is 10, and 5 is 15, and 6 is 21. So we have 21/6, which is, I guess I can cancel a 3 out of this and a 7. 7/3, which is 3 goes into 7 twice. No. 7 halves. I canceled wrong. 7 halves. Right. Because I canceled 3 from each of these. So 2 goes into 7 3 times and a half left over, 3.5. Right? Which is sort of halfway in between. Okay, so that's the expected value of a die. And similarly, we can have the expected value of some function of a random variable. And that's the sum over I of this f of x, I times the probability of I. Right, so we could say, the ith face, suppose you had 6 faces, but you, instead of numbering them from 1 to 6, you numbered them 5, 7, 12, 13, 27, and 91. Right? Then that would be your f of the face number would be that other number. And then you could similarly add up the scores times the probability. So you can think of the events as separate from their scores. Okay, so let's see. So the variance of a random variable. That says how far away you would expect a given instance of the experiment, that xi, to be away from the average of the experiment. Sometimes this expected value is called the mean, right? The mean score that you get on the die is 3.5. Now, if you think about it, right, this number is bigger than 3.5 and this number is less. So they sort of cancel each other. In terms of, if you just look at the difference, and then this difference would cancel that one, this difference would cancel that one, the expected value of the difference is 0, because you have positive differences and negative differences. But if you look at the square of the difference, then both of them will be positive. And like people talk about the root mean square error of a measurement or something, that's sort of said how the measurements vary on the average in terms of the squaring them first and then taking the square root. So that's called the standard deviation. And if we square it, that's the answer before you took that square root. That's going to be the variance. Sometimes I see variance of x instead of capital V instead of capital E. And what that is then is the sum of the value for all possible outcomes, the value of xi minus the expected value of x, this mean value, the 3.5 we had, squared. That multiplied by the probability of, that particular event. So this is, this squared quantity weighted by the probability. So this is what it really is. It's the expectation of x minus e of x squared. So I'm going to put extra brackets here. This now is a function of x. And I'm taking the expectation of that function. And that's what it really amounts to, right? Because this is a constant as far as this experiment is concerned. We pre-compute the mean, and then each experiment is a deviation from that mean. So this x isn't a variable in here anymore, even though it looks like it is here. So now I want to get some properties of the mean and the variance. So the square root of the variance is what's called sigma, the standard deviation. So first I'm going to say if x and y are two random variables, we can even say, or functions, on the same event space. Right, so in terms of a function, I was talking about printing those other numbers on the die. But you could think of printing two numbers on each die, right? One of them is x and one of them is y. And then what I want to show you is that the expectation of x plus y is the same as the expectation of x plus the expectation of y. And that's just algebra with the distributive law. Because e of x plus y we can write as the sum over I of the xi plus yi we get from the ith outcome times the probability of the ith outcome. And by the distributive law, this is the sum over I of xi pi plus yi pi. And I'm putting parentheses just to make sure this sum is over both of them. But then we can write this as two sums plus the sum of all the second terms, yi pi. And that's the expectation of x plus the expectation of y. Okay, so if we do that, then I can get, if you believe that proof, I could get another formula for the variance. Because what I'm going to say is the expectation of the quantity x minus e of x squared. Well, this thing I can multiply out as x squared minus 2x e of x, where this one is a constant and this one is the variable, plus 2 e of x, I'm not 2, plus e of x quantity squared. That's just re-expressing what I've got inside here. Okay, so now I can do, because of this rule, I can say it's the sum of these three things. So that means it's the expectation of x squared minus the expectation of 2x e of x plus the expectation of this constant e of x squared. Well, the expectation of any constant is equal to that constant, right? Because whatever that constant is, the expectation of it is the sum over I of that constant pi. And I can factor, I guess anytime I factor out an expression from a sum, I'm actually using the distributive law. Times the sum of the pi's, but because of that rule on the next board here that all the probabilities add up to 1, this is just going to be the expected value squared, that constant, because this is going to be 1. Now for this one, similarly, I'm going to factor out this constant 2ex, right? Because I'm going to write this as, well, why don't I think of it as, let me put the minus in front here. Is that going to make it any easier? No, it's not. Let me keep it the way it was. The expectation of this, as far as the events in question, this is x, and the 2e of x is the constant, the mean and the factor of 2. So I'm going to factor that 2e of x out, just like I did over here using the distributive law. And then it's the sum. Well, then it's the expected value of x, right? What's left is just x, and this is the expected value of x. So this term is minus twice the expected value of x squared. So I have minus 2 of them and plus 1 of them. So the answer is going to be e of x squared minus the expectation of value of x squared. So that's another formula for the variance of x. So instead of finding the mean and subtracting it, you can just, which would mean going through one loop to compute the mean and then another loop to, compute these deviations. You can, in the same loop, compute the mean of x squared and the mean of x, and then just square this one and subtract it from that one. Okay, so the last thing I want to discuss is the variance of the sum of two things. So if x and y are two random variables again, is it true that the variance of x plus y equals the variance of x plus the variance of y? What do you think? Let's take a vote. How many people think it is? And how many people think it's not? Okay, so some people know that it's not. A simple example of it's not being is suppose I make the two numbers x and y, I put it on each die face. I make x go 1, 2, 3, 4, 5, 6, and y go 6, 5, 4, 3, 2, 1. Right? Then the sum of x and y is always 7. And its average is 7, and its variance is going to be 0. But the variance of each of them, the book computes it by arithmetic, and I think the answer came out to be 2.9, certainly non-zero, right? Because, none of those die are exactly 3.5 numbers. So this isn't true in general. So when is it true? All those people who raised your hand, do you remember enough probability and statistics to remember in what circumstances it is true? No, the actual word is independent. And the two events are independent. So two, I guess that's really random variables. X and y are independent. If the probability, let me write it like this. I'm going to list the event inside by writing out x is equal to some value r and y is equal to another value s. If that probability, right, so we do the experiment. Remember I said event could be odd or even or anything I can make as what I'm classifying my outcome of the experiment into these events. And here's this particular event. I pick two numbers, and I say, what's the probability that this random variable x will come out to be that number, and the random variable y will come out to the other number? And that probability should be the same as the probability that x equals r multiplied by the probability that y equals s. Okay, so if I had two die and I threw them, and there weren't some sort of mysterious magnets connecting them or something where the first toss affected the second toss, they'd be independent, right? The probability that I get 1 on the first and 3 on the second would be a 36th, one of 36 equal chances. But even if they're not equal chances, if one die is loaded and the other isn't, so one die has a higher probability of coming up 6. If those dies aren't communicating, this fact will still be true. Whereas the fact that, the previous case I gave, the roll on the first number completely determines the roll on the second number. They're definitely not independent. So if x and y are independent, then I claim the variance of x plus y equals the variance of x plus the variance of y. So how am I going to do that in 2 minutes? I'm not going to succeed. Why don't you think about how you can use independence to prove this fact, and I'll prove it in class next time. Because otherwise, I'll run out of time today. And I already owe you a minute from yesterday, so now you've got that minute back.